Today we begin with a set of queuing problems. In our previous classes we have seen what is the importance of queuing theory, and apart from that we have also checked on the basic birth and death process, and thereafter we have seen the basic derivations for MM1 queues, and now it is also we did some problems of MM1, but we need to do some more problems to really clear our concepts on the queuing theory, particularly on the most important queue, that is that single server Markovian queuing process. Now, basically just look at this simple diagram. We have already shown it before, that there is an input source from where the customers arrive, join a queuing system. The queuing system consists of two parts. The first is the queue itself, and the second is a service mechanism. And from the service mechanism, where there are one or more servers, the served customers leave the queuing system. One of the most important thing to understand, particularly for the very basic MM1 process, is that the meaning of arrival and service distributions. You see, when we tell the arrival is 6 per minute, you see it is not really possible that the arrival is a constant 6 per minute. This 6 per minute is essentially is a mean rate of arrival. Is it all right? Mean rate of arrival of entities to the service station is, let us say, lambda per hour. So, what is the distribution? The actual number of arrivals, which will not be exactly 6 per hour or whatever is the value of the lambda at that point, it is actually following a Poisson distribution, right. So, this point has to be very clear. In the problem, sometimes we may be writing the arrival rate is 6 per hour following a Poisson distribution. What exactly it means? That the actual arrivals is 6 per hour, around that value, is not, it may not be exactly 6, but the mean value is 6, and these actual arrivals following what is known as a Poisson distribution. Service time, on the other hand, usually is expressed in the form of exponential distribution. So, what exactly it means is that the actual service time during the service period follows an exponential distribution. What is the mean of it? The mean service time of the service station is 1 by mu per hour. Earlier also I have said, and we shall see it further today again, that if the actual number being serviced per hour, if the service time is following an exponential distribution, the actual number being serviced per hour follows Poisson distribution with a mean service rate of mu per hour, right. So, one side is the service time, which is exponential, which is equivalent to the number being serviced is having a Poisson distribution. The same logic can be extended to arrival also, that if the number of arrivals in a given time follows Poisson distribution, then inter arrival time follows exponential distribution, right. So, these are the basic Markovian processes, and we must remember that. So, it is a kind of review, and now let us see three very important parameters, the L, the LQ, and your LQ dash, right. Three very basic parameters of average number of customers with regard to the MM1 system. The first one, as you can see, is we have already derived, that is average number in the system. Sometimes it can be also called the expected number, is L, which is defined as sum over n equal to 0 to infinity, because up to infinity is that is the queue space that we can have multiplied by NPN, right, where Pn is the probability values. Please recall, for an MM1 queue we have got some basic results. What are those basic results? Already we know that P0 equal to 1 by rho, P1 equal to rho times P0 equal to rho times 1 minus rho, P2 equal to rho square 1 minus rho, generalizing Pn equal to rho to the power n 1 minus rho, right. So, all these basic results are already known with us, and we also know that rho, that traffic intensity, is lambda by mu, where lambda is the rate of arrival and mu is the rate of service. So, these basic results for MM1 FCFS infinity queuing system, these basic results are already known. So, if these basic results are already known, the first parameter, that is average number in the system L, equal to sum of n equal to 0 to infinity, it is an expected value of the number, right. Since it is an weighted average, that is why that individual n's are multiplied by specific p values. What is the value of this? The value of this is rho by 1 minus rho, right. That is the average number in the system L. The second parameter, that is average number in the queue, right. Average number in the queue is LQ. What could be LQ? LQ, you see, at any point of time one person maximum could be in the service, because there is a single server, is it all right. So, supposing there are only one person in the system, that person will be in the service. If there is nobody, then obviously the question does not arise. But supposing there are more than one person, then that person will be in the service. If there are two person, then one person will be in the service and one person will be in the queue. So, you can understand that LQ now will be having a sum of n equal to 1 to infinity, then NPN, right. No, not really NPN. NPN basically it should be n minus 1 into Pn. Why? Because n is the number in the system and n minus 1 is the number in the queue, is it all right. So, since n minus 1 is the number in the queue, this term can be simplifiedly written as n minus 1 into infinity NPN minus sum over n equal to 1 to infinity Pn, right. Why n minus 1? Once again, because n is the number in the system, n minus 1 is number in the queue. Now, look here, n equal to 0 term is 0 times P0, that is 0 anyway. So, since n equal to 1 and n equal to 0 sum both becomes exactly same. And what is this sum, n equal to 1 to infinity Pn? This is nothing but 1 minus P0, because this is all the term other than P0. So, this is nothing but L, the first term is nothing but L and second term is nothing but rho, because it is L 1 minus P0 and look, P0 equal to 1 minus rho. So, 1 minus P0 equal to nothing but rho. So, this term become L minus rho. So, what is L minus rho? It is rho by 1 minus rho equal to rho square by 1 minus rho. So, this is the expression for LQ, rho square by 1 minus rho. Now, there is a third term which we also like to discuss in this context, which is the average number in the non-empty queue. Sometimes this also becomes an important parameter, average number in the non-empty queue, which we call as LQ dash. Now, what is non-empty queue? Non-empty queue is, let us say that in a particular queuing system there are say 10 people in the queue at a given point of time, but all of them get serviced and some more people join, some people again leave and everything. At some point of time we find that there is nobody in the system, right. So, let us say out of 1 hour there were somebody in the queue for some time, there are some other time when there was nobody in the queue. What would be that value? That value will be 1 minus P 0 minus P 1, right. Why? Because look here, what is the significance of 1 minus P 0 by minus P 1? You see, this is the probability that somebody in the queue. Why? Because you see, P 0 means system is empty, nobody in the system. P 1, 1 person in the system, and that 1 person in the system is really is in the service, because there is a single server and the person must be in the service. So, look here, only 1 minus P 0 minus P 1. What is 1 minus P 0 minus P 1? Let us work it out also. 1 minus P 0 minus P 1 equal to 1 minus rho minus rho into 1 minus rho, because look at all this formula. So, that would be 1 minus 1 plus rho minus rho plus rho square is nothing but rho square, right. So, if suppose rho is half, then rho square is 1 by 4. That means, if the busy period is 50%, then only 25% time there will be somebody in the queue. At other point of time there will be nobody in the queue. Is it all right? So, basically what we need to do, we have to wait for that, and LQ dash should be n equal to 2 to infinity, right, because 0 and 1 should be excluded, and this should be n minus 2 into P n dash. Why P n dash? Because the probabilities are modified based on, because P n dash is like a conditional probability. Let us write it here, P n dash equal to P n by 1 minus P 0 minus P 1, right. So, it is given the P 0, P 1 and minus P 0 and P 1, but what is that value? This value is nothing but P n by rho square, right. So, what really happens, that given that somebody is in the queue, so that is P n dash. So, that is the probability that should be used really for calculating the expected number in the non-empty queue. So, what you really get here is the LQ dash, but look here, one more interesting thing. If n equal to 1, then this term becomes 0 once again. So, that term has got no value. So, therefore, n equal to 2, even if you sum it to n equal to 1, it does not really make much of a difference, and this term essentially then become is equal to the LQ by equal to LQ by rho square, because already we have found out that Pn dash equal to rho square. Is it all right? So, the term essentially becomes the same, and as the term becomes the same, we find that LQ dash formula comes out to be LQ by rho square, right. And what is LQ by rho square? LQ by rho square equal to rho square by rho square 1 minus rho, because already this result is known. So, that gives us LQ dash equal to 1 by 1 minus rho, right. So, this is the third result. So, these are the three results which are so important in this particular thing. Look at the slide once again. L equal to rho by 1 minus rho, LQ equal to rho square by 1 minus rho, and LQ dash is 1 by 1 minus rho, right. So, these three results are we shall use, and let us look at their comparison in the form of a problem. See, in a service center, customers arrive randomly 10 per hour following Poisson distribution. There is only one server. The service time is exponential, and the mean service time is 5 minutes per customer. So, you have to find average number of customers in the system L, average number of customers in the queue LQ, and average number of customers in the non-empty queue. It is a very straightforward problem. All you have to do is find the traffic intensity, that is rho, right. Find the rho, and once rho is found, you can find out all the three parameters very easily. So, here is the computation. Look here, the arrival rate is 10, the service rate is 60 by 5 equal to 12, the utilization factor rho equal to lambda by mu comes out to be 5 by 6, average number of customers in the system is L equal to rho by 1 minus rho, which comes out to be 5, and average number of customers in the queue LQ rho square by 1 minus rho comes out to be 5 by 6 whole square by 1 minus 5 by 6. So, 25 by 6 or 4.166, and look what is LQ dash. LQ dash is 1 by 1 minus rho, comes out to be 6. So, one important question, why is LQ dash greater than LQ? LQ dash 4.166 and LQ is 6. Why LQ dash, that is 6, is greater than LQ? It can be understood in this way. You see, suppose Q is formed in this particular case, the rho value is 5 by 6. That means the utilization is 5 by 6. What is non-utilization? 1 by 6. Is it not? Again, 5 by 6, that means the Q is formed only 5/6 of the time. But what is rho square? Rho square is 25 by 36, right. So, 25 by 36 is the actual time out of 1, right, where there is some Q. So, when you are averaging the Q over a smaller period of time rather than the full period, obviously you get a higher value, right. So, basically while you average, you take out those data where the Q length is 0. If you take out those data, then the remaining Q will become larger. So, LQ is 4.166 and LQ dash is 6, that is why LQ dash is larger. Now, what is the importance of this? Sometimes you see we try to average things only what we see. Suppose in a particular counter, there are people, there are no people. If there is none, there is nobody in the system, obviously we may think that there is no Q. Let us only take data when there is some Q and then average it out. That figure is LQ dash, right. So, one should be very clear about these three parameters L, LQ and LQ dash. Let us look at some other problem. Now, this is an interesting problem about the arrival of planes. Arrival of planes at an airport is the mean rate of 20 per hour. the airport can land 60 planes per hour on an average in good weather and 30 planes per hour in bad weather. Obviously, all these data that we are talking about is in a peak period. So, now question is that when there is congestion, the planes are forced to fly over a field in the stack awaiting landing, right. So, there is a stack area, the runway is busy, the other planes that arrive has to wait, right. Wait where? In the sky, right. It has to move around and they will be awaiting landing. So, question is, how many planes should be flying over the field in the stack on an average in good weather and in bad weather, right, and how long a plane should be in the stack on the average in good weather and in bad weather. Now, the question, look at this diagram, now tell me which one is stack in this diagram and which one is runway and which one is the queuing system. Is it all right? See, the planes are arriving, the service begins when it is starting to land, that means when it is getting the runway and actually lands. So, the service mechanism consists of the runway. The queue consists, the stack is actually the queue. So, in this case we are really talking about the queue and not talking about the runway or the service mechanism. That means, we are basically asking for LQ and WQ parameters. This point has to be very much should be very clear. Sometimes the service is more important and some other time the system is more important. Sometimes the queue is more important, is it not? Suppose you are waiting to get into a movie hall. When you are trying to get into a movie hall, you are gone there to see the movie. So, seeing the movie is not something that is you are really worried about, because you actually have gone for that, right. It is the queue outside that is what you are not liking. But on the other hand, suppose you have gone to get a tool and you are waiting in the queue, right. How long you waited in the queue is obviously important, but actually what is more important is how much time you actually spend in the entire process, right. You spend some time waiting in the queue, you got some time you have spent getting the tool and then you come back. So, therefore, the entire time, in this case the system times, that is system that is W, that is the waiting time in the system, is more important. So, this must be understood in the appropriate context. So, again look here, in this case, in this particular example, this is the plain example. In the good weather, the arrival rate is 20 and the service rate is 60, whereas in bad weather arrival rate is 20 and the service rate is 30. So, what is the utilization factor? In this case rho is 1/3 and in this case rho is 2/3. So, if you compute the LQ is 1/3 square by 1 minus 1/3 comes out to be 1/6, right, and in the bad weather it comes out to be 2/3 whole square by 1 minus 2/3 comes to be 4/3. That is the average number of planes in the stack, that is LQ. And if you divide this by lambda, but please remember the Little's formula basically tells LQ by lambda bar. The lambda bar essentially means that if the lambda values are different over the period, then we must take an average and divide by that and not simply lambda. But most of the examples we are taking, the lambda is same all the time. So, lambda and lambda bar are equal, is it all right. So, that is why when we use Little's formula, we are just dividing by lambda. So, in this case what we find, the average waiting time in stack becomes WQ equal to LQ by lambda, and which comes out to be half minute, right, for the good weather, and in the bad weather it becomes as high as 4 minutes. So, you see the waiting time increases 8 times, but you see, you sometimes we tend to think that the airport can land 60 planes per hour, whereas it is now doing only 30 planes per hour. So, how this waiting time has increased by 8 times. A service has fallen by 2 times, but if you simply think it will be linear and waiting time in the queue will be also only double, it is not true. It has gone as high as 8 times. Reason is that even in good weather or the bad weather, even look at in the bad weather, the utilization factor is 2 by 3. That means there is 33% of time, that is 1/3 of the time, the system is empty, there is no plane. Is it all right? So, it is not that the all the time the planes are waiting, is it not? Planes are waiting for certain period of time, and when those times are accounted for, then this is happening. So, these points must be remembered, and please remember again and again I focus on this particular point, that the mean rate is 20 per hour, that is the arrival rate. The service rate has to be higher than the arrival rate. Only then the queuing problems will come to an equilibrium, and this kind of analysis that we are doing is meaningful. But if the arrival rate is higher than the service rate, then there is no equilibrium. If there is no equilibrium, the system is in transient stage, and in transient stage none of these formula is going to work, right. So, that means rho should be always less than 1, that is a very important requirement. Now, let us look at another problem, that in a service center only one person can get service. Any other arriving customer has to wait outside, as there is no place available inside. The customers arrive randomly at 8 per hour. The service is exponential and takes 6 minutes on the average. Find the probability that an arriving customer will have to wait outside, right. So, we have done one problem earlier, where we have seen that what really happens if it is when there is not enough facility available for the waiting customers. Please remember, it is not limited queue. We are not saying a customer who arrives will go away if there is no seat. It simply says that the customer will not be able to get a seat. This situation is different from another situation, where the person, if the system is busy, will go away, and that process is called balking. Is it all right? Anyhow, think about this problem, stop here, and we will continue from here in our next class. Thank you.